Okay, right. So let's continue our session of this afternoon. Our next speaker is Pavel Lushnikov. We talk about optimal canonical variable in free surface dynamics.
Yeah. First of all, I would like to thank organizers for organizing this nice event. So it's really nice, and also I'm impressed. I'm first time in Newcastle, and my impression was it's some industrial northeast part, but instead what I found, you just jump in a metro, right, and go to beach and enjoy the beach. And because already there's so many people ask about my swim yesterday, I Roberta. Yeah, you see, this swimming, it was really enjoyable. So I hope we're yeah, let me go back to science. I hope that organizers will consider in future years maybe do more on summer, right? Because why to go to Mediterranean? Why to go in summer to Florida? We can go here and enjoy this nice sleep. I mean, I really enjoy it. Okay, so this talk is dedicated to memory of Vladimir Zakharov. This is I decided to present our old work, who passed away just a little bit less than 1 year ago. So this work about ill-posedness of original Zakharov equations for water waves, and basically not since this old work, it was a lot of people noticing this ill-posedness, but from very beginning we even found constructive way how systematically way only by controllable perturbation theory, but with some non-perturbative tricks, what you will see later, to get rid of ill-posedness. And what happens, basically, it was, well, we did this work before war, and at some point I presented this talk at Landau Institute when we still traveled. Zakharov after that stand up and said, just, you know, of course I did with 1968 variables, but it's not, we need to do now a completely new way, but we never, unfortunately, managed to organize numerical simulations to demonstrate it. So it's kind of remains since I never presented on West except last time a few weeks ago in Baltimore. Okay, let me give some quick background. Many of you familiar with this. So we're looking for incompressible motion of fluid with free surface. So ideal fluid. So we have Euler equation, incompressible in gravitational field. Density we set to 1, so it's incompressible. Respectively, if we introduce potential flow, so V is a number of phi velocity potential, immediately we obtain Laplace equation inside fluid. Of course, well known. And when this first Euler equation results, if we factor out nabla, results in Bernoulli equation. So, but of course, here main difficulties come from free surface. So I consider I'm not restricting as in my usual talks to two-dimensional case. It's a full three-dimensional flow. So we have vertical z and x, y horizontal coordinates, and we will correspondingly parameterize surface as z as some function eta of x, y, and z. So time-dependent free surface. Now, all the linearity here comes from boundary conditions. First is a kinematic boundary condition, which tells if we grab fluid particle on a free surface, it moves with free surface. So mathematically, it can be formulated in 3D that material derivative of eta, our surface parameterization, is equals to vertical velocity, and is unit normal vector. And the dynamic boundary condition tells that if we set without loss of generality pressure outside of fluid is 0, so here I put air, but actually I assume it's vacuum. I neglect air. Then if we move on arbitrary small distance to inside fluid, we raise the pressure jump. If we take into account surface tension, this is exact expression, plugging into Bernoulli equation. As a result, we get closed equation where we completely exclude pressure because we need Bernoulli equation only on a free surface for this problem. We can easily recover pressure inside fluid, but for dynamics, we don't need pressure anymore. Okay, and then as a result of what we obtain, Laplace equation inside fluid plus kinematic and dynamic boundary conditions, we got closed set of equations. And Vladimir Zakharov showed that his famous work 1968, but actually original results all were published in his PhD thesis in 1966. So technically it was obtained even earlier, which is of course, which PhD dissertation is not easily available. I mean, it's in big libraries in Russia, but it's not published in like some quality journals. So basically, we state that we can introduce canonical Hamiltonian system for two variables. Psi, it's a Dirichlet boundary condition for phi, and eta our parameterization. And this is canonical Hamiltonian system, it's variational derivatives, and Hamiltonian, again, it's absolutely well known since 1966 or 68. That Hamiltonian is just total energy of a fluid, so kinetic energy. So we just integrate from bottom minus h to eta, and then integrate over z, and then integrate over xy with both r, it's two horizontal coordinates. And this is volume integral. But for potential energy, we have gravity term and surface energy term. Again, no approximation so far. It's already written directly in xy variables, surface variables. Okay, now we can immediately use Green's formulas to convert volume part into surface part for kinetic energy. So as a result, we're getting normal velocity. This is create some trouble because we know in terms of Hamiltonian variables psi, but we need to determine Vn. And mathematically, what it means, we need to find Dirichlet-Neumann operator for each moment of time, which relates Dirichlet boundary condition, so our psi, to normal velocity, which is, of course, Neumann boundary condition. So in other words, we have at each moment of time, we have to solve Laplace equation, which allows basically from psi recover normal velocity and advance in time our free surface. And what Zakharov did in this 66-68 work, he did this by perturbation theory, where a small parameter of is nabla, it is typical slope of surface, and this became one of his most famous work. I mean, integrability of NLS, it has highest citation, but it's perhaps second best known work, Vladimir Zakharov. Now, few words how we technically can derive this perturbation theory. We just can, for example, do Fourier transform over horizontal coordinates. Our Laplace transform Laplace equation will come to this, right? It's ODE in Z. But this is works if you're looking above flat surface. But our surface, it's some perturbed surface. So basically, we have to do Taylor series expanding from flat surface, where we can easily solve Laplace equation, to our curved surface. And this creates perturbation theory. So, for example, this type of terms shows up, and when this is for z equals to 0, now for this we have basically invert Fourier transform to go back from z equals to 0 to some z equals eta. Okay, and another notice which I will highly use in this talk, that of course if you do Fourier transform, it just can conserve Hamiltonian structure. So now it's a Fourier harmonics. So for them we have similar Fourier structure. We just doing Fourier transform in Hamiltonian. Okay, now I showed this slide again. I just give ideas without technical details. They are known, at least for this part. If we do this perturbation theory, which Zakharov did in 1966, we get Hamiltonian up to fourth order, so quadratic, third order, fourth order Hamiltonian. So for quadratic, for example, these two coefficients are corresponding with hyperbolic tangent k, and then with contribution gravity and surface tension. Cubic terms, fourth order terms, this is what sometimes we call analogy with physics matrix elements of this integral operator. We're just showing here. So A is just Fourier transform, inverse Fourier transform of k tangent A. So it's a linear integral operator here. And this notation, for example, 1 plus 3 means a Fourier harmonic for k1 plus k3. Okay, and when respectively we can do inverse Fourier transform, calculate variational derivatives, arrive for dynamical equation. So this is written here. This is again, it's all correspond to Zakharov results 1966-68. Now, some interesting observation, which we can get started to get something beyond completely standard thing. let's look for kind of oversimplified problem when gravity is zero, surface tension is zero, and look only for cubic terms in Hamiltonian. Well, we can immediately derive this system of two equations. It's surprisingly, this first equation is actually linear. And if we now restrict to 2 dimensions and introduce complex potential, so psi plus pi r psi, so r is basically finite depth version of Hilbert transform in 2D. So this will be nothing more than screen function. Then after some work, we can arrive to complex Hopf equation for this complex potential. So it's a principle that it's a complex here. Now we can immediately do simple analysis, just look for short wavelength instability. We assume that there is some typical scale at which in space and time our free surface evolves, and the same for speed. But when we're looking for k, extremely large. So we're looking for scales much smaller than any typical scales of evolution of free surface. So for these small scales, basically we can froze everything and look for local analysis, which immediately results in this dispersion relation. And here, AK is just part, our integral operator just replaced by function of k because k is very large. And here, this integral part of operator, but because sign here is arbitrary when you look along free surface, it's unavoidably we have instability. And this instability grows with k, so it means that we have ill-posedness in the system, we have arbitrary large growth rate for arbitrary large k. Of course, no nice dependence on the initial condition is possible in that case. Okay, and this is empirically, it was known for a while because numerical people were always to cope with problem, they just always introduce some artificial damping. Sometimes it could be just Fourier filtering, but it's always inevitable introduce some hyperviscosity. But we don't want to have this uncontrollable effect. And this is what we did. First, we solved this previous oversimplified problem. And basically for that, what we want to do canonical transformation from original variables, eta psi in Fourier space, to new canonical coordinate psi and new canonical momentum r. So for that, we just recall elementary course of analytical mechanics, which of course done for finite dimensional, in generalization for infinite dimensional systems, introduce generating function. So you see it as a standard like Landau Richard's book, it depends on new momentum and all coordinates. And then what after some work we found that we can write this term for generating function. In principle, we have freedom what to write, we just choosing to get something useful. As a result of that, we calculate with variational derivatives, which allows to recover all psi through r and eta, and new coordinate also through r and eta. Here actually it depends only on eta for this particular order of perturbation theory. And then after some work, we arrive just instead of complex Hopf equation to a real Hopf equation. So it means it's now well posed, everything looks good. Our next question on this work was, well, can we extend it to when we recover more physical things, surface tension and gravity? And answer is yes, and the remaining part of the talk I will give you. Stop switching, whatever reason. Sorry about this. Okay, actually start switching. Okay, sorry about this. Okay, so again, we look for short wavelength stability. Again, eta naught and psi naught, as already mentioned, were a slow function of space and time. Okay, now after some work, if we take into account for what the terms in Hamiltonian, we arrive to the following dispersion relation. It's kind of reduce this artificial growth rate. Yeah, and why artificial? Because after some analysis, we obtained that it's actually for very small scales, perturbation theory is violated. It's unavoidable here. So it's completely natural that we have troubles. The question how to fix them in a regular physical way, not introducing any artificial terms. So what we get here, basically this is estimate. So this term is neutrally stable, of course, but this term is unstable. And because of introduction of other terms, we have just this eta, which is our small parameter. So it reduces growth rate, but of course it doesn't matter because for large enough k, even with this reduction, it still probably is ill-posed. Okay, so next step was, first of all, for next step, let me in terms of technique. It was much more convenient for us to work directly with Hamiltonian than with linearized equations. So we just did directly in the Hamiltonian, we keep only quadratic terms in this perturbation, delta psi and delta eta. Again, all other terms will be higher order in terms of perturbations. So if second order in Hamiltonian, of course, in dynamical equation, it's actually written here, it will be just linear terms. So basically all physics contained in these coefficients A, B, F, and G. And if we calculate corresponding dispersion relation from this, again, linear equation, we immediately get this most general expression. Again, all physics stay in these constants. Well, the function of k were independent on the perturbation delta psi delta eta. Okay, now in particular, if we want to recover results from original Zakharov variables, then we found expression for all this ak, fk, and just plug in into this equation from previous slide, and after looking for leading order, we arrived to the same expression which I already showed you before. So it's by basically we kind of established technique which we work on remaining part of this work. Okay, and after that, we just looking down for general canonical transformation. So first two terms as I showed before, but now I'm adding fourth order terms. After some work, we realized we only need these terms r, eta, eta, eta. No more terms needs to suppress these ill-posedness. Now, work actually is quite technical because we did a lot of work. How to, because we have, of course, infinite freedom in trying to choose different with matrix elements. So, but eventually we arrive to this quite simple form. It's, you see, it's quadratic in K, quadratic in A. I remind you, A is our integral operator, which is K tangent K, hyperbolic tangent. And this alpha are our free parameters, which we choose for our convenience. Now, what we did in terms, if we would do straightforward perturbation theory, when basically using this trick with introducing convenient generating function, it's equivalent to take into account infinite number of terms of perturbation theory, but number of terms is always infinite. It's well known from these Feynman diagram techniques from quantum field theory, but basically we remove indirectly from this trick all divergent diagrams, which correspond to wave divergent Hamiltonian for large K, and correspondingly, this is what is called ultraviolet divergence in terms of quantum field theory. So we completely, if you try instead of generating function, do brute force, of course, it would be infinite number of terms. And basically, again, removing this infinite number of divergent diagrams, it means that out of infinite sequence of all perturbation terms, we choose some infinite subsequence which diverge. Okay, so first of all, we have, again, as I mentioned, it's technical work. I plug in with arbitrary alpha and beta, so for example, shown here, back into original Hamiltonian equations, do perturbation theory to keep terms up to fourth order and arrive just for general expression. Again, we don't need to look on all details, but for example, you see quadratic terms reminds what we have before. But higher order terms were modified by this alpha 1, alpha 2. Okay, and then do again the same analysis with the same type of quadratic Hamiltonian and calculate new dispersion relation, just all function A tilde, B tilde, F, and G were new ones. And what we arrive after that, again, expression is large, so I'm not showing it directly, but I will show you result on the plot. So on the plot, there are two coordinates, alpha 1, alpha 2. It's our arbitrary parameters. And what we found that for very small, in the limit of basically zero nonlinearity, so almost flat surface with infinite small perturbations, this dashed area in this parameter space, alpha 1, alpha 2, will be well posed. No short wavelength instability at all. Now, if we increase nonlinearity, this region dash area starts shrinking. You see, this is for 0, this is for 0.025 typical slope. Then we increase further, so it's a sequence of increasing. For large enough nonlinearity, it's a 0.13, it shrinks to 0. So there is no complete magic bullet for strong enough solutions. Eventually, system will become ill-posed again. But it's well known in people who do simulations of oceanic turbulence that actually this type of slope in terms of Ka, for some of you who are familiar with this terminology, is immediately results in wave breaking. So basically, this nonlinearity is very large, and we start, if we reach this nonlinearity, that probability of wave breaking becomes of the order of 1. So, of course, no chance that perturbation theory, originally starting from 1968, or our modification since when, will work for wave breaking, and still perturbation theory. But basically, our message that if we stay below this initial condition, when we have often wave breaking, system becomes well posed, and we can now work safely without introducing any artificial hyperviscosity. So I believe this is way how to go for general, for example, ocean turbulence simulations. But still, if anybody interested, I will be happy to provide details how to do simulations. You know, just matrix elements were a little more cumbersome, but not terribly. I mean, our intermediate calculation longs, but at the end, when we arrive to these matrix elements, they're extremely compact. It's not terribly worse. I mean, maybe twice more terms than in original Zakharov 68 equation. And the only thing, you know, extra thing which will be needs to be done, basically we run simulation in new variables. Then at the moment when we want to recover physical field, we need to do by iteration of these integral operators to recover original physical variables. So it gives some burden, but I believe not terrible one. And to conclude this talk, I'd like to mention it was really an honor for me to work with Vladimir Zakharov. I originate from his school, although technically I'm his scientific grandson, because Evgeny Kuznetsov, who was my PhD advisor, he was a PhD student of Zakharov. So it was actually first work which we did with Zakharov, and later we work a lot about conformal variables, but it's really was absolutely great influence of on me and working in his school. In his school, it was really honor for me. Okay, thank you.
We have time for questions. So any question for Pavel? So I actually have one. So maybe I missed a step in the computation, but before you managed to obtain a real Hopf equation.
Mm-hmm.
So with this additional term, how would the equation look like?
Well, it's you know, it's some calculation. Let me maybe give. Sorry. Yeah, I mean it's all published, but it's requires some work, unfortunately. So basically, this equation up to cubic nonlinearity.
Yeah.
After some work, if we restrict to 2 dimensions, then we can represent. So, for example, this analog of Hopf transform, it basically represents function which is sum of extension, analytical extension in upper low complex half plane from real line of x. And then what happens for this equation if we use such expansion into upper and low analytic parts? Basically, in terms of Fourier transform, we split part with positive k and negative k. There is some trick which basically make equation closed for p plus and p minus. So this function analytic in low and complex half plane. This is why we arrived to this equation. And here I kind of cheat a little bit, actually, it's system of 2 decoupled equation for p plus, p minus. Now, if we do this do this conformal, no, sorry, not conformal, this canonical transformation to new variables that are shown here. Here, what happens that we can completely remove from equation, the structure of equation now is different. We can completely remove real part. So basically our psi and keep only stream function and then equation for stream function. I know I'm not answering you directly, but it's a computation. It's not terribly, this part is not super long. And I mean, a really long computation for half order Hamiltonian. So I know I'm not answering you directly, but this is kind of, you know, just straightforward calculation. As soon as you found this generating function, it's all straightforward.
Okay.
Yeah. Sorry for
No,
very
no,
direct
no,
answer.
Thank you, Pavel. Any other question? Yes, again.
Computation appears in the case of machine.
Yeah, yeah.
Is there any relation between your work and the work of the curve? Of course, it's not even case and information asked and so on.
Well, first of all, we published with Zakharov in 2021 some work where we study approximation, but well-controlled approximation when solution in complex plane. So if we do an relation from fluid to outside of fluid, when we have short branch cut. Short, that means distance between branch point much smaller than distance to real line text. In that case, we also derive the same type of complex Burgers equation. But this approximation, what Karabut, I mean, I know well works of Karabut, they did it in really auxiliary variables. So that I believe in some limits, there is a relation to our derivation for short branch cut, when branch cut is really short. But in principle, because we use in our variables, it's a different story. So it's a good question. It's not the same. There are some relation, but it's definitely not the same. And actually, I don't remember. Maybe in Karabut was even real Burgers equation, or maybe complex analysis. You rather point anyway, because at some point, I mean, I'm still doing this work. It's possible to completely bypass this step for Karabut results for this complex Burgers equation and kind of start constructing even larger family of solutions, just technique which is more general, because it's kind of, you know, doing this in these auxiliary variables with complex Burgers, it's really strict to class of exact solutions. But advantage, of course, what Karabut got, it was arbitrary nonlinear solutions, which was absolutely great result.
Okay, so yeah.
When you use canonical transformation, you truncate the system, right? So two equations might be different.
Yeah, absolutely different. So basically, to go back, but in some sense, relatively similar. You know, there are this also called Zakharov variables, right? When you exclude for gravity waves, you exclude non-resonant terms, sometimes called from A to B variables. But to go back from B back to physical variables, when you can recover sine eta, it also, you need to do it, solve integral equations typically by iteration. So basically what we're doing when we're doing this inversion, we just keep the same order of perturbation theory. I mean, it's a little extra hassle, but again, I think in terms of computational cost, it's not adding much, it's added, but in programming, it's adding extra steps. But again, we always keep both order Hamiltonian. We're not going any further, except what I mentioned, we indirectly remove all divergent terms in higher order terms, but only the divergent terms, this ultraviolet divergence.
Okay, so let's thank Pavel again. Thank you.